Okay, hello, students. I'm going to go over with you today logarithms, a new type of function, the last function that we will be introduced to. And because it is towards the end of the year is, of course, almost over, then I'm just going to kind of go over just about everything about logarithms. The only thing that we won't cover in this video is solving logarithms, and but we will talk about graphs of logarithms, some basic properties, then graphs of logarithms, then transformations of logarithms, parent functions as well, and then simplifying rational expressions. For example, how can you add two logarithmic expressions together? How can you subtract them? So those are some of the things that we will cover through the video. But before we can really talk anything about logarithms, we just need to have a basic understanding of a logarithm. For example, how do you read a logarithmic expression? And you can see here that logarithms are written in the form of log base b of x. Okay, that's how you would want to read that statement, log base b of x. So for example, if your base was 5, then you might say this is log base 5 of x, or it doesn't have to just be x. It could be x plus 5, x, or all kinds of sorts of things here. It could be fractions, and but this is the basic way a logarithm is written. You may have noticed, using calculators as long as you have. I'm sure you've at least seen the log button on the calculator. So that is something that we can use. This one that's right next to it also is also a logarithm. This one right here, this ln, that is actually a special type of logarithm. And there are a couple of special types of logarithms, as a matter of fact, which is also covered here in this first slide. The couple of different special logarithms. You have the common logarithm, which is a logarithm, just like this one is here, but the base is 10. Okay, the base is 10. It is not written as the subscript of the log, though. We always have these things in algebra, these things that we are supposed to know that are there, even though they're not written there. For example, something just as simple as writing a variable. Well, that really means that there's a 1b if you just write a b. Other types of things, when we do a square root, we're supposed to understand that that's the second root, even though we don't generally write the 2 there. Some other examples of numbers that we're supposed to do, even in something like 1b, where it's understood that means that the exponent would be a 1 if that b did have an exponent. So there's all sorts of things that we're supposed to know that they're there, even though they aren't written there. Even something like writing two variables next to each other, mn. Well, that really means m times n, even though that multiplication sign is not written there. Okay? In this case, we need to understand, we need to know that when we see a log without a base, we need to think that's the common log. That's the log that has really a base of 10, even though it's not written there. Okay? The other one is called the natural log. The natural log is a logarithm with base of e. We talked about e when we did exponentials a little bit. There's actually 13.4, I believe, was all about the number e and exponents with a value of e. Remember, e is a number. E is approximately 2.71828. And so this natural logarithm is a logarithm that has a base of 2.71828. It is actually not written using the abbreviation log. It is abbreviated ln. I don't know why it doesn't seem to make sense why it would be ln if it's the natural log, but that is in fact what it is. So we need to understand that when we see a logarithm, I can see I actually have a little error right here. But when we see this log x, that means that we understand that that's the same as log base e, and that's the mistake there that I have. I had a b there when I needed to have an e right there as the base of this logarithm. Okay, so try to make that look maybe a little better, maybe not. All right, so that's base e. All right. So, those are a couple things that we need to remember as we go through here. Something else that I might add in here, b needs to be a positive number. B needs to be greater than 0 and a whole number. So really b is whole numbers. B greater than 0 and a whole number. Okay, so we won't be seeing a base that is a negative number in logarithms. They don't exist. Okay. All right. So let's move on. Here we got something, just to kind of get us familiarized a little bit with logarithms. We want to look and see if we can't figure this out. It says below is a puzzle similar to the one that is more than 21,000 years old. I won't read the whole thing to you. You can do that. But we got some clues here. So the log base 2 of 8. Okay, notice how that is read. Log base 2 of 8 is equal to 3. Log base 5 of 25 is equal to 5. Log base 3 of 27 is equal to 3. And log base 10 of 10,000 is equal to 4. What we want to see if you can do is figure out why. Why is the log base 2 of 8 equal to 3? So it's kind of like a puzzle, you got to figure out, what's the pattern? What's going on here? Why is log base 5 of 25 equal to 2? And I do provide you this way to transform. Actually, a logarithmic expression can be written as an exponential expression, okay, or equation. An exponential equation can be written as a logarithmic equation, and vice versa. And this is how you do that. You just you follow the letters. Okay, you got a base here, and the logarithm is actually the base here of this exponential. You see the x, what this is equal to, what this logarithm is equal to, is actually, when it's written as a exponential, that is the exponent here of the base. And the A is this number here. So it's kind of like backwards. It's kind of a little backwards as far as where the letters are. In this case, A is what this is equal to. In the case of the logarithm, x is what the equation is equal to, or the logarithm is equal to. And that, again, would be the exponent in the exponential notation. So that can help you figure this out. As far as what the pattern is right here. As a matter of fact, I'll go ahead and do A with you down here. But if you wanted to figure out what x is here, the best way to do it would be to rewrite this expression as a exponential function, because we understand exponentials better. We know, we can figure out things with exponents more than logarithms because we're not as familiar with logarithms. Well, let's change this to an exponential equation. Well, our base here is 2 of this logarithm, and you can see that base number of 2 here is actually the base number of the exponential. We call this number the base, and this, of course, x is the exponent, but b is the base. So we got a base of 2. Okay, well, the exponent of this 2 is what the logarithm is equal to. So this would be an x power here, because that's what this logarithm is equal to, and then that's going to be equal to 32. Okay? Well, 2 to the what power is 32? 2 to the what power is equal to 32? Well, the answer to that would be 2 to the 5th power. That would be something that you could, just do a check and guess here, and you might try, a 3 for x and a 4 for x and a 5 for x, and once you got to 5, you would actually see that that is equal to 32 if you were using a calculator. Okay, so I'd like you to try to see if you can't follow that model to do B, C, and D on the quiz that you'll take after completing the video. I guess I didn't mention that at the beginning, but there is a online quiz that you will take once you have completed the video. Okay? So, moving along. Alright, so here we got some graphing of a logarithmic. We'll look at a parent graph here. We're also going to look how a logarithmic and an exponential equation are related. We looked on the last slide a little bit already about how they're related and the fact that one can be written as the other. An exponential can be written as a logarithmic and vice versa. But we want to look more at that relationship, a closer examination of the relationship between logarithmic equations and exponential. Okay? So what we have here is we have the graph of e to the x. Okay, that's the blue graph here, and then this is the graph of the natural log of x. Remember, that's L in x. You want to actually read that as the natural log of x rather than saying L in. You want to call that the natural log of x. If you also remember from the first slide that that is the same, that is equal to a log with a base of what? With a base of e. Okay? So that's log base e of x is what the natural log of x is. Okay? But we need to just call it the natural log of x. All right. So do you notice a relationship or how they are associated here in the graphs as we look at the graphs? I also have a table for e to the x for values from -2 to 3, as you can see here, and we also have values of the natural log of x from -2 to actually 4 here. Notice that for values -2, -1, and 0, that the natural log of x is undefined. Okay, meaning you can't take the natural log of -2 or -1 or 0, which should tell you something about the domain of the natural log of x. Which we'll actually look at on the next slide. Okay, so what we want to notice, so are they reflections? Okay, so this is the big hint right there. Are they of reflections, and over what line? Well, they are reflections. You should be able to see that, but the line that they are reflected about is the line y is equal to x. Okay, that's this line right here. Not right there. Let's see here. I'm going to adjust this line here to get it to match up with the natural, or the line y is equal to x. See if I can get that there. Turn it a little bit, move it. Okay, that's pretty close to the line y is equal to x. What you should be able to visually see and visually concur with is that they are reflections of each other over the line y is equal to x. As a matter of fact, if I was to look at a couple of specific points, say the y-intercept here, the y-intercept of e to the x is at 0, 1. That is the y-intercept of e to the x. For the natural log of x, the x-intercept is at 1, 0. So you can see the coordinates there have been switched. The table will also verify that for an x value of 0, the y value is 1 for e to the x, and for 0, or excuse me, not want to look at that, but at x equal to 1 for the natural log of x, the value of the function is 0. So that confirms that 0, 1 is on the graph of e to the x, and 1, 0 is on the graph of the natural log of x. Okay, so they are reflections of each other over the line y is equal to x. All right. Well, what does that mean? Okay, are they reflections? Yes, they are reflections over line y is equal to x. Okay. So what does that mean? Well, if you would remember back to, we've talked about these situations before where a function is a reflection of another function over the line y is equal to x. And in fact, what that means is that they are, what are they? Let's write it in big letters. The graphs of a logarithmic function, logarithmics and exponentials, people, those functions are, write it big here, those functions are not big enough. Alright, that still isn't really big enough, but they are inverses. Gotta write it bigger than that. Okay? So the inverse, so what I'm saying here is that the inverse of a exponential, any exponential function, is going to be a logarithmic function. The graph of a logarithmic function has an inverse that is exponential. Okay, so if I was to take the coordinates, let's see here, I want this to go away now. Let's just undo that. Okay. So if I was to take these coordinates here, the -2 and the 0.1353, and switch those. Remember, inverses have values, x and y coordinates, that are switched. So if I switch those x and y coordinates, then because this is the graph of the exponential function, then 0.1353 comma -2 is going to be a point that is on the graph of the natural log of x. And so to verify that, see at -2, this value right here, this x value right here for the y value of -2 is approximately equal to 0.1353. So remember, my point here is to remember that inverses means that the x and y coordinates have been switched. So if I switch these x and y coordinates, then I will obtain the points that would be on the graph of the natural log of x. Okay. Also point out that natural log of x would be considered a type of parent function for logarithmics. Okay. And so the next piece here is, let's look at the properties of logarithmic parent functions. Let's look at the properties of a parent function. The parent function I chose is a logarithm that has a base of 5. So I want to point out that the base number, for every base number, that would be considered a separate parent function. So just like we saw with exponentials, there are many different logarithmic parent functions. Okay, but these properties are going to be the same for every parent function, whether the base is 5 or the base is e or the base is 10 or some other number. Okay, But what is the domain? Well, we got to be looking at the x's here. Okay, so the x's, of course, go across the graph here from left to right. And what we would want to notice to help us figure out the domain is that the graph doesn't actually go over here to this side of the graph. It doesn't go to the left of the y-axis. Well, the reason why it's important to understand that to help you determine what the domain is because the x values on this side of the graph are negative. -1, -2, -3. So because they are negative and the graph doesn't go over there, then we can say that the domain is x's that are greater than 0, or, if we wanted to use interval notation, then we could say from 0 to infinity. And also, why just 0? Why not include 0? Why not say x is greater than or equal to 0 there? Well, the graph does not actually touch the y-axis. As it goes down, it's going to get infinitely close to the y-axis, but theoretically never be able to touch it. And so we can say that it's not going to include 0. The domain will not include 0 because it does not touch the y-axis. All right, well, what about the range of this parent function? Well, let's see. Now we're talking about y, so now we're looking at the graph vertically. Okay, we want to figure out what we can see about the function vertically. Well, what we can see is that it does go below the x-axis, and that would be important to realize for the range because the values that are below the x-axis are y values that are negative. Okay, all these coordinates down here and all these in between, every point that's on this curve below the x-axis are all going to have negative y coordinates. And when talking about the range, that's what's important to be figuring out. As it continues on, it does go above the x-axis, so all these y coordinates are going to be positive. I can see that it's growing slowly, but still these y values are still going to be positive. Okay, and then just keep on getting to be larger and larger positive y values, although they do increase fairly slowly. The y values aren't getting large very quickly, but they are going to continue to increase. Well, what does this tell us about the range? This would tell us that the range is x's that are greater than negative infinity and less than infinity. In other words, negative infinity to positive infinity. I can also switch this to set notation right quick. If I just add here a vertical line here, the x in front and the brackets, not a very good looking bracket on that side, but on a bracket on each side, now I've been able to write the range. I'm doing range here. Look what I did. Oh no. I made that a x. Well, I'm talking about range, and so that should be a y, as well as I should have a y here. But you can see there that now I've been able to write the range in set notation rather than just using inequalities, and also in interval notation. What about the y-intercept? Well, kind of already talked about this a little bit when we were discussing the range. It actually doesn't touch the y-axis. That means this function has no y-intercept. So I'm just going to say NA for not applicable. X-intercept, it does cross the x-axis, and as you can see here, it crosses the x-axis at the point 1, 0. Also recall that no matter what this base number is, that would still be the same for that function. All logarithmic parent functions are going to have a x-intercept at 1, 0. Is it increasing or decreasing? Well, it's increasing. Okay, and for small values, not only is it increasing, but we can talk about how it's increasing. And for small values of x, so if you look at these x values that are between 0 and 1, this function is increasing very rapidly. It's almost a vertical line. It's going so fast. The y values are increasing so quickly that it almost just looks like this is a vertical line right here, rather than something that has a little bit of a curve to it. And then it about I don't know. I'd say x equal to 1/2. The rate of growth begins to slow as it curves out and becomes flatter. And as these x values are getting larger, the rate of growth is decreasing. So it's still increasing, but the rate that it's increasing at is decreasing as the x values get larger. So it is increasing, and we can also should analyze, as we just did there, about how it's increasing. And then we go on to in behavior. Well, for in behavior, we want to say that as, or we can say, there's different ways you can kind of say the same thing, but as x's, I'm going to start with negative infinity. Well, as x's, x's can't go to negative infinity because we've already said that x's have to be positive. So I can say as x approaches 0, though. As x approaches 0, we're calling this one f of x, or f1 of x. I'm just going to call it f of x. Then I'm going to say, so as x approaches 0, f of x, that's the values of y, basically, are approaching. What are they approaching? Well, as this curve gets, so as this curve curves this way, the x values are getting closer and closer to 0. So x's, as it curves down, is approaching 0. Okay, as it curves down. Well, what's happening to the y values as the x's are getting closer and closer to 0, meaning that the function is getting closer and closer to the y-axis? Well, these y values are getting to be more and more larger and larger negative values. So in fact, what's happening to the y's here is they are approaching negative infinity. As this curve goes down, it's getting closer and closer to the y-axis, but it keeps on going down where the y's get to be bigger and bigger negative numbers. So f of x is approaching negative infinity. Okay? And then the other side of that, or what else? What other n do we have? This thing, I guess, has two n's, so to speak. But on the other side, we can say that as x approaches infinity, well, what's happening to f of x? Well, this is this direction, so this would be where the x is as you go out to the right and just continue on and on forever. Then that's x is going out to infinity. Well, what are the y coordinates doing? Well, they're getting larger too, and again, they're getting larger very slowly, but they do continue to get larger and larger and larger. So therefore, we would want to say that f of x goes to positive infinity. Okay, you probably did not realize that but for the exponential functions, the range is what the domain was, and the domain was what the range was. Because again, these are inverse functions. So the domain of e to the x, the range, not the domain, the range of the natural log of x. And the range of the natural log of x is the domain of the natural log of x. So the range of e to the x is the domain of the natural log of x because they are inverses. And on the end behavior, those are related as well, as x's, well, we won't go into that, but I do want to again stress that these are, that logarithms do have inverses that are exponential. Okay? Alright, so let's look at some transformations. Okay, talked about transformations with every function that we've approached this year, and so natural logarithms aren't going to be any different. Alright, but we should be able to go through this, hopefully at this point, somewhat quickly, and I'll provide you a couple examples. Even without even to look at any graphs, we should be able to answer these. Okay, so our parent function in this case is going to be the log of x. Recall that means that the base is 10. This is the common logarithm. common logarithm. The base of 10 is not written there, even though it is understood to be there. Okay. But that's not going to really be vitally important. We just have to look at this and realize that this is written in function notation, not actually applied to the specific, not actually applying the transformation to a specific parent function yet. Then this is showing inside addition. So f of x is equal to log of x. So f of x plus 2 is equal to log of x plus 2. So again, that shows inside addition. Well, how does inside addition affect the graph? Well, it shifts it to the left, as we should hopefully by now kind of be able to remember for the most part. If not, you do still have your transformation sheet to look at. And then for 13, we've got f of x plus 2. So this is showing in function notation, again, not applying a transformation to a specific function yet. This is representing outside addition. When I actually apply that type of transformation to this specific function, then we would show that outside addition by putting the plus 2 outside of the parentheses that surround the x. So that's log of x plus 2. That's outside addition, and that shifts the graph up. Okay. One more I'll go over here with you guys. Let's look at number 15. We got a few things going on here. We've got outside multiplication by -4, which will have two effects on the graph. It will reflect it over the x-axis and vertically stretch it by a factor of 4. And we have inside subtraction by 3, which will shift it down, not down, to the right 3. And then we have outside addition by a half. So vertical compression by a factor of a half and reflection across x-axis. So it looks like reflection over x-axis, vertical stretch by a factor of 4, and translated a half a unit up. It doesn't look like this includes the shift that should have been 3 to the right. But I am going to say that this one here is G. Okay? So that should also include the statement that it shifted to the right 3. Okay, so see if you can't figure out the rest of those. Actually, you just have 14 and 16 to see if you can determine which ones those go with. Okay? So transformations, use your transformation sheet. You can use your calculators as well to help you figure those out. All right? So transformations, we've done them. If you need some help, certainly ask for some help, but I think that we have a strong understanding of those. Alright, so last thing is the properties of logarithmic expressions. Okay, we're going to try to see if we can discover some of the properties of logarithmic expressions. Alright, so I'm going to use the calculator here. Let's see, I'm just going to go to where you can just see the handheld, so I get a smaller screen. What I want to do is I want to do the log for each of these values of x that are in the table, and round these answers to the thousands. That's the thousands place is the third number after the decimal. So let's do that here. So the log of 1, so I can use the log button. So I want to go to a regular calculator page. Just going to start a new document, regular calculator page. Actually, no, let me do this with the graph, so that way I can automatically have the values that I want to know about through the table. Okay, so log base. I didn't actually have to write the base there. If I left that blank, the calculator would understand that that is a natural log. So log base of, what is the first one? 1. Okay. No, I want to put an X there. Sorry. I want to do this just with an X and then look at the table. All right. Um, so log base 10 of 1 times X, which is still like log of X, even though the 1's still there. So tab. Let me go back up and just delete that. It's the same, but okay. So I got log base 10, the log of X. All right. So table, Control T. And so we got the 0, which is already filled out there. Bring that back up. Okay, I found this program that will allow me to tell what another program to stay, on top of all the other programs. So let's see if I can get that to work. Okay, so give me just a second here. Okay. So I should keep it on top so I can just get these numbers off of here. Oh, look, that didn't work, did it? Try again. Document 15. Huh. Yeah. Oh, shoot. All right. Come on. Okay. So it doesn't want to seem to quite do that like I would like it to. So I've got another calculator here at my desk that I'm going to use. So log of X. Okay, so for when X is equal to 1, we'd be at 0.301. So this is going to be 0.301, X equal to 3, 0.477. Okay, 4, 0.602, 5, 0.699, rounded off. These are all rounded off to the thousandths place. 699. 7.778 for log of 6. The log of 7 is equal to 0.845. Log of 8 is equal to 0.903. Log of 9 is equal to 0.5954. 0.954, and the log of 10 is equal to 1. Okay. So if I was to type in the log of 2 plus the log of 3 in a calculator, I do want to do this on the calculator. So the log of 2 plus the log of 3. Okay. So let's go to calculator. Okay, so log of 2 plus log of 3. Okay, and as we go through this, you'll see something. Hopefully, you see a pattern emerge. And what we want to do is see if we can't come up to a conclusion by understanding that pattern. So 0.778 there. So 0.778. Log 2 plus log 4 is next. Okay, so log of 2. I'm just going to go back up here and plus log of 4. So I just need to change that to a 4. That's 0.903. 0.903. Okay. Well, rather than doing it like that, I can also just do it with the actual numbers I already have. 0.301 is the log of 2. The log of 5 is 0.699. And if I was to add those up, that would be 1, 0, so that'd be 0, 0, 0, 1. Okay, so it'd be actually equal to just 1. Log of 3, that's 0.477 plus 0.477. Okay, log of 3. And that's actually equal to 0.954. Calculator can verify that those do add up to a 0.954. Okay. Well, have you noticed anything here about these answers? 0.778, well, that's what the log of 6 is equal to. Right? You look at 0.903. Do we see that anywhere? Well, that's equal to the log of 8. And the 1, that's equal to the log of 10. And log of 3 plus log of 3 is equal to the log of 9. So what is going on here? So that the log of 2 plus log of 3 is equal to log of 6. So that's what we can actually say here. We actually say that this is equal to the log of 6. This is equal to the log of 8. Okay, and so from that pattern, what you want to do is try to see if you can't fill out what the log of m plus the log of n is equal to. Similarly, you can fill out the values for log of 10 minus log of 2. So log of 10 is 1. Log of 2 is equal to 0.301. And see if you can't figure out a pattern for this so you can create a rule for that. And then I also have included a third rule, which is p times the log base b of x equals log of base b of x to the p. Excuse me, I'm sorry. Okay. And so just to verify that rule real quick, so let me give you an example that I could use to demonstrate this. So what it would be saying is that if I'm going to write something in this form here. So if I write the log of 3 squared, then what this rule is saying, so I've written something like this. Well, what this rule says is that that power, that exponent, can be written as a product of that logarithm. So in fact, I can take that 2, write it out in front of the logarithm, and multiply that by the log of 3. So I have moved that to the front of that, and that's what it says is possible to do. Well, to verify that, using the values from the table, the log of 3 squared is equal to 9. Well, the log of 9 is equal to 0.954. And 2 times the log of 3, well, log of 3 is equal to 0.477. And it is actually true that 2 times 0.477 is, in fact, equal to 0.954. So that does end up checking out as something that would work when I actually use numbers from the table. Okay? So that is a property of logarithms that we need to know as well. But I want you to try to see if you can't figure out these two on your own. Okay? And actually, I will go ahead and tell you what it is. See if I can't get it to. Okay, this might be it right here. This must be it right here. Alright. Okay, so here is these three properties of logarithms written in a formal fashion. The product property of logarithms states that the log base b of m plus the log base b of n is equal to the log base b of m times n. So if you just think about that, the log base 10 of 2 equals log base 10 of 3 is equal to log base 10 of 2 times 3, or log base 6, which is what our log of 6. Log of 2 plus log of 4 is equal to log of 8, based on that rule. When we are subtracting logarithms, then we actually want to divide those two numbers. Okay, so this gives us a way to simplify logarithmic expressions by being able to take two logarithms that are being added and write that as one logarithm, or taking two logarithms that are being subtracted and writing those as one logarithm, where we divide the m and the n, and also being able to take an exponent and write it out in front of a logarithmic statement. Okay, if you could make sure to complete all the parts of this slide, and make sure that you turn that in and take the online quiz, then that will complete your the assignment for this for logarithms. Thank you very much. If you have any questions, please let me know, and I'll help you out as much as I can.